Welcome to this video on solving systems of equations using matrix inverses. You'll see here on the screen that there are three equations here with x, y, and z, and we're trying to solve for the numerical values. What is x, what is y, what is z? In order to solve them, there's many techniques. One of them, the content of this video, is about matrix inverses. The first thing you want to do on a problem like this, if you're going to use matrices, is you're going to want to make a matrix equation out of it. Now, what does it mean for one matrix to equal another? Of course, it must mean that that number equals that number equals that number, and that number equals that number. Each of the parts must equal each other for the two matrices to be equal. So first, set up a matrix equation. Then, someone developed a really cool trick that I'm about to share with you, and it involves factoring the left side of the equation. Let's remember what it means to factor. Factor means to turn something into a multiplication or product. How can I do that with the left side of the equation? Well, it turns out I can take this and replace it with these two factors. On first glance, it probably appears to you that I took all the numbers or the coefficients out of the equations, put them in one 3x3 matrix, and just put x, y, z in the second matrix. And when you're solving these problems this way, it's okay to do that. But I'd like to go off on a side note here for a few minutes about why it's okay to do that. To prove to you that this is the factorization, I'm going to actually multiply out my alleged factors and show that they do in fact equal the original matrix. This isn't mandatory when you're doing this as a solving technique, but I think it's worth watching nonetheless. So looking in the upper left corner, let's remind ourselves, how do we multiply matrices? We multiply by doing what's called a dot product of one row and one column. Remember, a dot product means that we multiply these, multiply these, multiply these, and add the results. But when we do that, we get 3x minus y plus 2z. Second, we take this row and multiply by the column in the same fashion of a dot product. This times this, plus this times this, plus that times that, which of course works out to this quantity. And you can see where I'm going here. Likewise for the third row times the column, 0 times x, plus 1 times y, plus 2 times z equals this quantity. This work that you see in the upper left corner is not mandatory for the solving process, but it's a justification for the factoring. Again, many students get a little confused by that justification, and they simply want to follow the procedure shown in red here, which is to put the numbers in one matrix and the letters in another. And while that doesn't really have any deeper understanding attached to it, it is valid nonetheless. So once you have factored the left side, one thing that we can do to solve for x, y, and z is to multiply both sides by the inverse of that 3x3 matrix. If you have not learned how to take a 3x3 matrix and find its inverse, which is, by the way, its own extensive process, on my prior videos, it's a 4-step process, but everybody has a slightly different way of doing it. If that's not something that you are familiar with, you're going to have to go research that. I recommend just looking up a matrix inverse video, either mine or somebody else's. But that's a whole process in and of itself that's not included in this video. The benefit, however, of multiplying both sides of the equation by the inverse matrix will be shown here in the next few minutes. Because when you multiply the first two matrices here together, it turns out you get what's called the identity matrix, the one with ones on the main diagonal and zeros everywhere else. Now you could actually multiply these matrices out to get this. It's a nice way to confirm that you calculated the inverse properly. But assuming we did calculate the inverse property, this will always happen. The very definition of inverse matrices are two matrices who multiplied together equal the identity. So I know I'm going to get that result, but I honestly, just for practice, will always multiply that out anyways. It's a nice way to check if you actually got the inverse right, the fact that their product is the identity. As far as the right side of the equation goes, those matrices have to be multiplied out. The work is not shown here, but if you haven't yet studied how to multiply matrices, that's another topic that you have to know to be able to do this. And I recommend, if you don't know this process, that you check that out on a video for multiplying matrices, either mine or somebody else's. So at this point, we have now solved, or I shouldn't say we've solved, we've now gotten this equation down to a point where if I could work out the left side, I would have solved for x, y, and z. But as you may know about multiplication by the identity matrix, it doesn't change anything. In other words, the identity matrix times anything is that matrix itself. And by doing this process of multiplying both sides by the inverse, we've hereby isolated x, y, and z into a single matrix, and now we know that x must be 7, y must be that number, and z must be that number. And that's the solution to this problem. And thank you for watching this video.